So I put this on a 9C final once, and I shouldn't have. Even though I told everybody it would be on there, I still shouldn't have. It just takes too long to work it out. But I thought, well, since I'm not going to do it to you, I can still give you a chance to think about it. Lots of times, people will put together two coils of wire that are wound the same way. If they're wound the same way and have current going around the same way. If you think about it, use the right-hand rule. If current is going around like this, then the magnetic field is going to point to the right due to that coil there on the left. So it points through the coil along the x-axis, points to the right all the way along the x-axis due to that coil. The magnetic field due to the second coil, wound the same way, current the same way, also points to the right along the x-axis. So those two magnetic fields add together. They're both pointing in the same direction, they add together. This is called a Helmholtz pair of coils. And so how would you find the magnetic, well, I'll talk about why you would do that in a second. How would you find the magnetic field along the x-axis? And the answer, I hope, is that you've already done this problem. That the Biot-Savart law lets you calculate if, what is this called? R. Let's say I take a little piece of this dl, which is really r d theta, where theta is an angle around here. Theta is an angle around there that I'm going to eventually integrate around. The magnetic field out there, due to this dl, okay, there's a distance to that point. So there's an r vector from dl out to that point. If you use the right-hand rule here, the current is coming toward me up there at the top. If I look at this thing, looks like when you're up at the top on the y-axis, the current is coming toward you. If the current is, if dl is a vector pointing along the z-axis and r is right here, then what do I get for, let's see, something like a magnetic field that is perpendicular to r. So the magnetic field due to that dl is going to be something like that. When I integrate around this whole thing, the parts of the magnetic field that are not along the x-axis are going to cancel out. So all of the y components, y and z components of the magnetic field are going to cancel out. You'll only have an x component left. And so all you need to do is add up all the x components. So I might as well just put that. What's the x component of the magnetic field due to that coil? And I'm just going to write down Biot-Savart just so I'll have it here. And look at all of the pieces. Well, there's the mu 0 over 2 pi. There's the current. Now, I have n loops. So I want to integrate once around. And so I'm going to have to multiply by n because every loop is going to contribute. So the total current around there is really n times I, because there's n loops and there's I in each loop. dl across r gives me a vector, in a db vector in that direction. I'm going to need to divide by r squared. Well, this r right here, the magnitude of that squared is, well, it's just made up of this capital R. This is r, by the way, the radius of the circle. So it's made up of this capital R and this value of x wherever I am. And so r squared is capital R squared plus x squared. So that's all of these pieces that get me the vector, but I want the x component. And the x component of this thing is the part that's right there in the x direction. And so I'm going to have to know this angle. I'm going to call that angle alpha. I'm going to have to know that angle so I can take the cosine of that. So I can multiply this vector times the cosine of that angle and get the x component. What is this angle? Well, I'm pretty sure it's that angle there. And so the cosine of alpha I'm going to need right there. But the cosine of alpha is just going to be what? R over r squared over the square root of r squared plus x squared. I think that's a cosine of alpha. So that's what I need to multiply by. And so I'm going to want an r up here and an r squared plus x squared to the 1/2. And to get the total, this BO and sub r is the differential magnetic field due to a differential piece of the loop. I'm going to want to go all the way, integrate all the way around the loop. And so, oh, I forgot something. dl. What is dl? dl is r d theta. I'm going to go all the way around theta. And so I need a dl, which is r d theta. Once I put all of those pieces together, I'm going to want to integrate theta from 0 to 2 pi. There's no theta dependence here, so that's not a problem. It's just 2 pi. So this whole mess of a thing is the magnetic field in the x direction along the x axis due to one of the coils. I should have stopped there. Unfortunately, I put the Helmholtz pair there, and that means there's another coil. And so now you have to figure out what the magnetic field for that other coil is. You've already calculated it, but now you've shifted this thing over by r. So I'm not going to worry about what you do with that. I think you just substitute r minus x for x for the other coil. And then you add the two together, and so that's roughly what you would do. The only part that's important is using BO sub r for a loop to find B sub x. Yeah?
So cosine of alpha will be, how is it r, isn't it r over the magnetic field at that point for that dl?
dB, this is cosine of alpha, I hope. So if this is alpha, is that okay? First of all.
B r squared plus x squared.
If this is alpha, then the cosine of alpha is the adjacent side, which is r, divided by this length of the hypotenuse, which is little r, and little r is the square root of r squared plus x squared. Here's r and there's x, the triangle. So unless I could be wrong here, but hearing no general acclaim that I'm wrong, I'll just move on. I think that that's cosine of alpha. So just quickly, why would you do such a thing? Well, what is B total as a function of x? Well, it drops off as x gets bigger. So B total as a function of x does something like that. Due to one coil, due to the other coil, B total as a function of x is going to be dropping off in the other direction. If you add these two together, I shouldn't have called it B total. I should call this B left and call this one B right. When you add these two together, you end up with something. You end up with a magnetic field that doesn't change very much with position. In fact, the point of building these is to produce a magnetic field in the center which doesn't change very much, which is pretty constant in the exact center. It's to produce a uniform magnetic field from just wires. You can produce uniform magnetic fields in different ways. This is one way. Anyway, this is simply practice using Biot-Savart law to integrate and find a magnetic field, and that's all I really wanted to say regarding that problem.